Hello, my name is Dominick Rowan, and I'm a senior in the Science Research Program at Byram High School. The title of my study is Determining the Frequency of Jupiter Analogs. Since the beginning of extrasolar studies, the question has been, how common is the solar system? In order to answer this question, it's important to identify the defining characteristics of our solar system, the first of which being long-period Jovian planets. Jupiter, Saturn, Uranus, and Neptune all reside in long-period orbits. In the inner annulus, the terrestrial planets are of a small mass. In recent years, planetary formation and migration studies have pointed towards Jupiter as being the cause of the development of the solar system structure. Jupiter initially formed at an orbit of around 1.5 astronomical units, where it began to migrate inwardly. At some point during this inward migration, the formation of Saturn, another gas giant planet, resulted in the creation of a mean motion resonance between the two planets. This has the effect of reversing Jupiter's migration direction, so it is now migrating outward. Jupiter left a profound impact on the inner annulus by increasing the rate of collisions between smaller bodies of rock known as planetesimals. As the rate of collision increased, there was less mass of rock available for terrestrial planet formation, ultimately leading to small mass terrestrial planets in the inner annulus. Therefore, Jupiter can be said to be the catalyst for the development of the solar system structure. Calculating the frequency of Jupiter-like planets, known as Jupiter analogs, is a precursor to calculating the frequency of solar system analogs. In order to detect exoplanets, there are two primary detection methods, the first of which is the transit method. The transit method monitors brightness variations for stars in the Kepler survey. As a planet passes in front of a star, a dip in brightness can be observed in the form of a light curve. In total, there have been 1,258 planets detected with the transit method, making it the most used detection method. However, there are several weaknesses that make it unfit for my study, the first of which are false positives. False positives are signals that appear to be planetary but are due to some other source. For example, an eclipsing binary produces a light curve similar to that of a transiting exoplanet. In addition, transit probability decreases as semi-major axis, or the distance between the planet and the star, increases, meaning the probability to detect longer period planets is lower. Selection effects also dictate that larger planets closer to the star are easier to detect with the transit method because they block out more of the star's light. In fact, the average period of a transiting exoplanet is only 25.5 days. Since Jupiter analogs have periods in the range of 5 to 15 years, this method is ineffective. Thus, we turn to the radial velocity method. The radial velocity method quantifies the Doppler shift in the spectrum of a star to produce a velocity graph. As a planet orbits a star, it exerts a gravitational force, causing the star itself to move around the system's center of mass. This movement is reflected in the spectral lines, which shift due to the Doppler effect. As the baseline of observation increases for a radial velocity survey, longer period planets are detectable. Since many surveys have accumulated baselines of up to 15 to 20 years, the detection of Jupiter analogs is a viable option with the radial velocity method. This graph, taken from our publication for the Astrophysical Journal, plots exoplanets detected as grouped by period and mass. Transit detections, labeled in blue, mostly center around short-period planets. Alternatively, the radial velocity method has capabilities to detect longer period planets, including those in the boxed region, which represents the Jupiter analog parameter space. However, some aspects of that black box for Jupiter analogs is still empty. Thus, we turn to a detection limit calculation to quantify the probability that a Jupiter analog was missed. In 2011, Wittenmeyer et al. Used a detection limit calculation in conjunction with data on 254 stars to calculate that the frequency of Jupiter analogs is 3.3%. My study aims to provide a more accurate calculation on the frequency of Jupiter analogs by using more precise data on a larger number of stars. The first objective of my study was to identify and constrain the planetary system of a new Jupiter analog orbiting HD 32963. The second objective was to calculate the raw frequency of Jupiter analogs using data on 1,122 stars from the Keck Observatory. The third objective was to correct this frequency for detectability using a detection limit calculation. After independently contacting my mentor, Dr. Stefano Meschiari of the University of Texas, I learned to use both the R language and the systemic console. These were crucial tools in all three objectives. In Objective 1, I evaluated periodograms, created radial velocity plots, and used statistical measures in the systemic console. In Objective 2, I created a script to detect and constrain Jupiter analogs. In total, I created over 350 lines of code between the objectives. An example of one of the scripts is pictured here. In Objective 3, I created another script in the R language to correct the frequency for detectability. I also worked with my mentor to develop probability expressions. But first, let's move into objective 1. HD 32963 is a G-type star, very similar to the Sun. The mass is slightly larger, and the effective temperature slightly higher than that of the Sun. The age of this star is 2.5 billion years, and the metallicity is plus 0.08. Therefore, HD 32963 is a Sun-like star. All observations were taken using the higher spectrograph, located at the Keck Observatory in Hawaii. For HD 32963, 109 observations were taken between January of 1998 and January of 2014, giving a baseline of 16 years. All observations followed the traditional method of an iodine cell being placed in front of the spectrograph slit to ensure wavelength calibration could occur. I first created a periodogram to plot the highest spectral density estimates within the dataset, where I identified the planetary signal at around 2,300 days. I then constructed the radial velocity plot to plot the best fit line, labeled in black. I was able to identify the semi-amplitude, the eccentricity, and the period of the exoplanet. Using statistical measures, I derived the rest of the planetary parameters to be as follows. Key parameters of note are the period at 2,372 days, and the mass at 0.7 mass of Jupiter. Therefore, HD 32963b is a new Jupiter analog orbiting a Sun-like star. It is one of only 27 Jupiter analogs detected to date. This discovery was made in the midst of the original objective of my study, to calculate the frequency of Jupiter analogs. In order to do this, it's first necessary to define the parameters of one. For this study, a Jupiter analog represents an exoplanet with a mass between 0.3 and 3 mass of Jupiter, a period between 5 and 15 years, and a low eccentricity, less than 0.3. I first created a script in the systemic console using the R language to detect and constrain Jupiter analogs. The script would first create periodograms for every star in the sample, isolate low false alarm probabilities, restrict for Jupiter analog parameters. I then visually verified the best fit solutions. The result of this process was 8 Jupiter analogs within the 1,122 stars, including the planet from objective 1. The resulting raw frequency is 0.71%. In order to create a more accurate calculation of the frequency of Jupiter analogs, we calculate the detection limit to assess the probability that a Jupiter analog was missed. This was done by creating synthetic planets over an array of period and mass combinations within the Jupiter analog parameter space. Each synthetic combination was injected into the original data as a new planet, where it was attempted to be recovered. If a synthetic planet is recovered, an actual planet with those same parameters does not exist in the system. It would have been recovered. Alternatively, if we were unable to detect a synthetic planet, an actual planet could have existed that was simply missed. Thus, this needs to be taken into account to create a more accurate calculation of the frequency of Jupiter analogs. In total, 320,000 synthetic planets were created for each star in the sample. The script was run on the Lone Star supercomputer located in Austin, Texas. Using probability expressions derived from Whitmire et al., we achieved a corrected frequency of 3.0%. This graph plots detectability averaged over circular orbits. As expected, as period increases and mass decreases, detectability goes towards 0. In addition, we found the median recovery rate for Jupiter analogs in the 5 to 15 year range to be 22%. However, if we increase this to the detectable period range of 18 years, the median drops down to 19%, indicating that longer period Jupiter analogs are currently not as detectable with Keck radial velocity data. Our results are consistent with previous estimates, specifically those of Whitmire et al. However, a limitation in our study is the detection of longer period Jupiter analogs. In fact, the longest period Jupiter analog we detected was one of 11.55 years. Keep in mind that the upper period range is 15 years. To bring back this graph from the review of literature, microlensing and imaging, labeled in orange and green respectively, both have the ability to detect longer period planets. Thus, these methods could be used in a future study to detect longer period Jupiter analogs. Since we identified Jupiter as a catalyst for the development of the solar system structure, this study is a precursor to determining the frequency of solar system analogs. Since we use more precise data on a larger number of stars, this study represents the most accurate calculation of the frequency of Jupiter analogs to date. Finally, this study is their first to report HD 32963b as a new Jupiter analog orbiting a Sun-like star. I'd like to thank my mentor, Dr. Stefano Meschiari, as well as the Lick Carnegie Exoplanet team and my science research teachers for their support. I'd also like to thank the Siemens Foundation and George Washington University for making this competition possible. Thank you.